Yeah. Okay, so good evening, everyone. Thank you very much for coming for our seminar today. So, and it is my really great pleasure to introduce Professor Sidney Morris, or Sid. So that's how we were calling him in Ballarat. So Professor Morris is really well known in Australia, partially because he was working at many Australian universities. So at the moment, he is emeritus professor at the Federation University and also La Trobe. But he was working at the University of Queensland, Wollongong, and that's, if I just, tell you all the places where he was working, we probably will not start today. So it's really a lot of places. And Sid is also editing the Gazette of the Australian Mathematical Society. So that also makes him really well known. And also, I should say that the research interests of Sid Morris, topology, so not quite optimization, but Professor Morris was working at Federation University, well, it was University of Ballarat at that time. And I think all the optimization people who worked at Federation at that time were really enjoying his talks. And I would probably anticipate that this is something that's going to happen today as well. Okay, so thank you very much. So Sid, and now the microphone is yours.
Thank you, Nadia. Now, I will try to share my screen, which should be straightforward, but nothing is always straightforward. Okay, so that's now shared. First of all, I'd like to thank the organisers for inviting me, and Nadia in particular, who asked me to speak. She actually suggested I speak on some work I did on Kolmogorov superposition theorem, but I'd spoken on it a couple of times in other contexts, and I thought it might be a change for me, thinking just selfishly to speak on a more recent piece of work on Ramanujan's approximation of n factorial. And even if you don't find the mathematics particularly exciting, I hope you will find some of the anecdotes and things around it interesting. And really, it does lead to an optimization problem. That is, what is the best of these many approximations and how can you improve it? So I leave that as a comment. So let me, as soon as I can get the next page to come. Early last year, as Melbourne went into lockdown for the pandemic, and at a time when I didn't know Melbourne was going to come up with a record, namely for the longest period in lockdown of any city in the world, I decided I needed to do something to keep myself sane, or at least the same as I was. And so I decided it might be fun to write a book on probability theory in the style of my Topology Without Tears, which is widely distributed. And so the book is meant to be comprehensive on finite probability spaces and suitable for anyone who's done first-year mathematics. That was the plan, and the book now exists, in at least in first draft form, online. And as I worked on it, I ran across Stirling's approximation for n factorial and various proofs for that, because I was looking for a proof to put in my book. And I found that there is also many finer results related to this, including proof result of Ramanujan. And so eventually I wrote a paper on tweaking Ramanujan's approximation of n factorial. And that's at least in archive at the moment. So let me begin with this probability. About in the 1500s was a very colourful character called Cardano. And he wrote a book on casting the die. He even has in that book a section on effective cheating methods. So now I know you'll go out and get the book. Cardano was both a physician and a mathematician, and he was regarded as one of the most influential of the times. He was also a physician. He supported himself through medical school on winnings from gambling, using his understanding of probability. So if you ever feel mathematics is not useful, now you can point to this example. Now, Cardano was born a bastard, and as such, when he graduated from medical school, he was not permitted to be registered as a doctor in Bologna, where he lived. And so he had to move somewhere else to a small town where he could practice medicine. Over time, by the way, he became so well known as a physician that he was called upon by royal families throughout Europe to help them. He's known more properly for his book Ars Magna, which is just a great art. And it's a book on algebra in Latin, the language, the educated language of the time. And what he aimed to do was write in that book all of the algebra that was known in ancient times by the Babylonians, the Arab mathematicians, etc. Not the Chinese, unfortunately, but and so it brought to Europe all of that mathematics, and it's regarded as very important. Now, we know that from Babylonian times, they knew how to solve quadratic equations, but cubic equations was how to solve them was not known. Indeed, it was rather more than this. There are Christian writers at the time who said cubic equations cannot be solved because the cubic represents the Trinity. And if you could really understand the cubic, you could understand the Trinity, and that's absurd. Anyway, that problem was solved by Scipione del Ferro. But it should be understood that at that time, it wasn't publish or perish. These days, it's publish and perish. But it wasn't publish or perish. What they used to do was find ways to solve certain problems and then keep them up their sleeve. When they were applying for university jobs, there was sort of a competition between the, if you like, the shortlisted applicants, and they would each give each other mathematical problems to solve. And if you had a method for solving something the other guy didn't know, then you probably get the job. Now, Cardano's student Ferrari solved the quartic polynomial equations. And as we all know, quintics, solving quintic equations was around for a couple of 100 years after that, before it was shown by Abel and Ruffini that there is no method for doing it when you're talking about solutions in rationals and surds. So Cardano's book had the solution for cubics and quartics for the very first time. Now, that book also was the first to have imaginary numbers or complex numbers one should understand at this time, even negative numbers weren't properly understood or known. They were sometimes all fictitious numbers, and of course zero was thought to be completely useless. Why would you need a number for zero? Anyway, this book also had material on binomial coefficients and the binomial theorem. Now, a French writer, nobleman, Bombada, amateur mathematician, he called to the attention of Pascal a problem concerning a popular dice game. The problem was about whether or not to bet even money on the occurrence of at least one double six during 24 throws of a pair of dice. And it was thought that this was a good bet, and in fact, it's not. So there was an exchange of letters, this led to, between Pascal and Fermat, and this really was the early steps in the development of the mathematical theory of probability. Huygens, who was a teacher of Leibniz, learnt about this development of mathematical theory of probability by Pascal and Fermat, and he himself wrote a book, The Value of Chance in Games of Fortunes, which is arguably the first printed book on probability. He was very much influenced by Newton's Principia. This Huygens was no slouch. He invented the pendulum clock, and he discovered Saturn's moon, Titus. De Moivre was a French Protestant, a Huguenot, who studied mathematics in Paris. When he was young, he was there with his parents. He was influenced by Huygens and by Newton's Principia, and unfortunately, he had to leave France because the Huguenots were persecuted by the Catholics. And so he sought asylum in England and stayed there, in fact, in London, for the rest of his life. He didn't get a university position, but he worked as a private mathematics tutor and consultant to gamblers. He became a friend of Halley, of Halley's Comet, and of Isaac Newton and James Stirling. And in fact, Halley helped him get some of his work published. So the second printed book on probability was The Doctrine of Chance by de Moivre in 1718. Now, in his research on games, he needed a good approximation for 2NCN, for that combination, where n may be quite large. And as you can see, since this involves 2n factorial, n doesn't have to be particularly large because that before that gets out of control. Even today, if you choose n big enough, and it doesn't have to be that big, calculators, etc., can't handle it. So he was looking for an approximation for that, 2NCN. So he proved that n factorial, which is all you need, can be approximated by Cn to the n to the plus a half, e to the minus n. Certainly something you wouldn't immediately think. If you're looking for approximation of n factorial, why should it involve e? This constant c he didn't evaluate, but it was a number of about 2.5. His friend James Stirling, Scottish mathematician, proved that that constant c is actually root 2 pi. And so Stirling's approximation is this n factorial is asymptotic to root 2 pi n on e to the n. Now, we should understand what this means. N factorial goes to infinity. The right-hand side also goes to infinity. So what we're talking about is the limit as n goes to infinity of the left-hand side on the right-hand side equals 1. So Stirling's approximation is good, in fact, very good for large n. But as you'll see in the next table, it's actually surprisingly good even for small n. So even when you have n equals 2, it's only 4% wrong. And by the time you're at 10, n equals 10, it's less than 1% wrong. And by 100, it's 0.08%. So it's a pretty good approximation. And if you look at it graphically, I plotted the n factorial in the black dots and the curve, that Stirling approximation, and the eye doesn't see that the points are not on the line. Now, I couldn't find a portrait of Stirling, but there is this plaque to the Stirlings in the garden of Dunblane Cathedral. Stirling's approximation was published in his book, which you see there, in 1764. So let's just have a look at a concrete example where n is a fairly large number to see how this approximation pans out. So assume in a particular country there are exactly 1 million births in 2020. Also assume that the probability that a baby is born biologically male is 0.5. What's the probability in 2020 that there will be exactly 500,000 babies born which are biologically male? Now, of course, it's not hard to guess that it's going to be pretty small, the probability that it's exactly that. But let's use Stirling's formula to approximate this number. Clearly, the probability is up. 1 million C 500,000 by a half to the million. And these numbers are rather big for a calculator. So let us use Stirling's formula and see what that says. And lo and behold, a lot of cancellation. You see 2NCN is 2 to the 2n by 1 on root pi n. Now, of course, 2 to the 2n you can calculate easily using logs or whatever. So the 1 on root pi n is a very manageable thing. So let's have a look at it. It comes out to be 000079788. And so we've been able to avoid calculating 1 million factorial and 500,000 factorial squared. As I said, obviously the number is very small. Finally, I mentioned that the actual number to that number of decimal places is equal. So as I said, the Stirling approximations are pretty good, and you can immediately see that for large numbers, you get rid of such an incredible amount of work. There are literally hundreds of papers that deal with applications of Stirling's result, that deal with extensions to Stirling's result, improvements, I would say, and a variety of proofs. I think one of them I quote and use published this paper as the n plus first proof of this result. So more recent or results that are relevant I've talked about here. There is Burside in 1917. Now this is the famous Burside from group theory, who, because group theory was not very popular in Britain in his time, and so late in life he took up probability. He wrote a book on probability, probably the first in English. It's not a very profound book, and his calculation on his improvement on Stirling's approximation is also not very marvelous. There's Gosper in 1978, Mortici in 2011, so there's still activity in this area. The extraordinary Indian mathematician Ramanujan, in the last year of his life, gave a remarkably better asymptotic formula. Unfortunately, this was in his notes, which weren't available to the public. However, I think it was George Andrews who spent quite some time putting that material together, and certainly he was at University of New South Wales working with George Zecherich and so on, and they found this result of Ramanujan. Ramanujan didn't include a proof of his approximation claim. He just gave numerical reasons for this to be true. As I said, his approximation is substantially better than all of those which appeared after him for the next 80 years. Of course, his result wasn't known. For example, when n equals 1 million, the percentage error of Ramanujan's approximation is 1 million times better than Gosper's. So it's definitely a damn good result. In 2013, my colleague, Australian mathematician Mike Hirschhorn from the University of New South Wales, who was very much into Ramanujan and probably helped develop that at the time Andrews was visiting, and the Costa Rican mathematician Mark Villarino proved the correctness of Ramanujan's claim, at least for positive integers. And you'll see what I mean about that later. But he was able to give a proof as distinct from just numerical indication. So what am I going to talk about today? So in recent years, there's been several improvements on Stirling's formula by Nemes, by Windschitl, by Chen. And the presentation today will show how all of these asymptotic results can be easily verified. I didn't say easily discovered, but easily verified to be true. How Hirschhorn and Villarino's argument, I will show, allows a tweaking of Ramanujan's result to give a better approximation than Ramanujan's. I then present out of the air, yet different result by tweaking Ramanujan's thing further. And Chen's asymptotic formula is better than all of those mentioned above. And the new asymptotic formula I present is comparable with Chen's, at least for n equals 1 million. Now, let's make the problem a little bit harder than Stirling had before we indicate a proof. Obviously, n factorial is only defined for positive integers, but the Swiss mathematician Bernoulli, Daniel Bernoulli, from the famous Bernoulli family, which there were many, and he was of the second generation, and Goldbach asked, can you actually extend this definition of factorial from positive integers to a wider class? Euler succeeded in 1729, refined it a bit, and in 1730 he proved that for x, any positive real number, you can define gamma of x, the gamma function, to be the integral 0 to infinity t to the x minus 1 e to the t dt. And gamma of n is n minus 1 factorial for any positive integer n. Now, in fact, this is true for more than just the real numbers. You can positive real numbers, it's for complex numbers with positive real part, and there's analytic continuation involved. I'm not going to go into any of that. Now, having an extension of the definition of factorial to gamma function, Laplace's extension of the formula of Stirling's formula to the gamma function. Laplace was a French mathematician, a very famous one, 1749 to 1827. So what do we get? Well, we get exactly what you might hope for, that is gamma x plus 1 is asymptotic to x to the x over e to the x, root 2 pi x. So it's an immediate extension to positive real numbers of the result of Stirling's result for natural numbers, for positive integers. Now, I'm going to give a proof of that result of Laplace, and I wanted to say a little bit about proofs, so I hope this is at least a little entertaining. Some proofs are described as short, others as informative, and yet others as elementary. Now, when we say short, it's self-explanatory. We mean, you know, it can fit on a page or less or whatever it might be. But what you invariably find in short proofs is somewhere in that proof, they use some very powerful result, which really isn't well known or isn't at the level of the other things you're doing. An informative proof is what we all hope for in one sense, because when you go through the proof, in the end, you understand the theorem better. An elementary proof is one which uses minimum background knowledge. And I will focus on Michel's proof from 2008 of the Laplace's theorem for the gamma function. It uses only calculus from, say, first-year mathematics. You don't use double integrals, really. You don't use complex integration. There's nothing of that style. So it's quite elementary. My aim is to show you that it's elementary, not for you to follow every one of the many calculations, because in the end, it's not very informative. Now, this notion of proofs being elementary or short or informative, Hungarian mathematician Paul Erdős, that's a photograph I took when I visited Calgary when he was there. My Erdős number is 2. I tried to get it to 1. He and I did work on a problem together, but we didn't solve it. The Hungarian mathematician Erdős coined the terms proofs from the book. So there's these different kinds of proofs, and we've talked about proofs from the book. Now, Magna and Ziegler wrote a book called Proofs from the Book. They talked to Erdős about it. Erdős actually thought it was a wonderful idea and gave them a list of things that might be included in the book, and some of those are. And the book is dedicated to Erdős, who often referred to the book, in which God keeps the most elegant proof of each mathematical theorem. I think about 1985 or something like that, Erdős gave a talk in which he said, you don't have to believe in God, but you should believe in the book. The book actually is illustrated by Carl Hoffman, who's in our audience today, and it sold a zillion copies, and it's translated into several languages. There's one piece of elementary mathematics I need to just mention before we get started, and that is what's called the error function, the integral from minus infinity to infinity e to the minus x squared dx is root pi. Now, you may know this triviality, or you may not know it, so I decided I would just pull it out. This integral is called the Gaussian integral after Gauss, who published the integral in 1809. It's also known as the Euler-Poisson integral, after Euler and Poisson worked on it, and it was first evaluated by Laplace, who I mentioned before, using a change of variable and single variable calculus. By the way, on the Eiffel Tower, you may or may not know this, there are 72 names of eminent French scientists, engineers, mathematicians. Their names are engraved, and this list, 72, includes Poisson, Laplace, Napier, Cauchy, Lagrange, and Coriolis. Probably other people you've heard of too. So now let me go to the proof of this Laplace's version of Stirling's theorem. I'll try and give an idea of how the proof hangs together, but it goes on and on. Anyway, so we're trying to do something with the integral minus 0 to infinity f of x dx, where f of x is x to the t e to the minus x. So we introduce this set A, set of x such that mod x minus t is greater than or equal to t on 2, and we look at the characteristic function of A. And then we can write gamma t plus 1 instead of as the integral f of x dx as the integral from t on 2 3t to 3t on 2 f of x dx plus the integral from 0 to infinity ga of x f of x dx. And you'll see after a moment's thought that that's true. What we want to focus on first is this red term, the first part of this integral, the integral in this first part of equation 1. And I just get some things you note. We defined what this set A was. We notice very quickly that 1 is less than 4x minus t squared on t squared. We're going to do some inequalities, and eventually we're going to show what? We're going to show that that red integral tends to 0 as t tends to infinity. So gamma z plus 1 is z gamma z, etc. So 2, 3, 4, 5 is straightforward. Looks like my voice is not going to hang out, not going to last. Anyway, so now we consider the absolute value of 1 minus gamma t plus 1 times this integral. As I said, we're focusing on this red integral from the previous page. And when we look at it, we just basically gather terms, put in the inequality that I said about x belonging to A, and lo and behold, there's nothing profound in anything that's written there, straightforward calculations, and we get 1, may have said something incorrect a moment ago, but never mind, we'll get there. We get this absolute value of this integral is 4 on t squared t plus 2. So as t tends to infinity, this thing tends to 0. So these two things are equal, the 1 and this other term. So what we get is the limit of 1 on gamma t of this integral is 1. I think I said 0 a moment ago, which was wrong. So that integral is 1, is just pure calculation. So we have that fact now. Now we're going to do some change of variables to proceed. And we're going to put x equals y root t plus t and define h of t, y to be equal to that thing. And we just have to look at what happens to the limits of integration. X is t on 2. This becomes minus root t on 2. X is 3t on 2. This becomes that. So now, let's have a look at the integral of ht of y. So we just make the substitutions using our definition. All of those are just straightforward, simple calculations. And so we now have, from our previous result, the previous result being that that limit is 1, we now have the limit of t to the t root t over that is 1. Now we need a little bit of Taylor series. It's a first year topic, so I'm not afraid to use it. Log of 1 plus x we can write out. and as a Taylor series, and we're going to compare the log 1 plus z to the first two terms in the Taylor series, and now we're simply going to get that the difference is less than the sum from 3 to infinity mod z to the n on 3. Now, by the way, we remember that in all of these Taylor series things, we can work out what the error is, the error term is, and later on we could improve what the result we have by working with those error terms. So what we now get is the difference between log 1 plus z and the first two terms of its series is less than 2 on 3 z cubed. Now we'll see what u and v we're going to define, but let's just do a little bit of calculation. Mod EU minus e to the v, where we're going to define u and v soon. We're going to get that, it's like a bracket's missing there, is less than or equal to that. So if we put z equals y on root t, we obtain a bound here, log 1 plus root 2 over this, but minus that is less than that. I'm quite aware that I'm going through this fairly quickly, but as I said, unless there is some particular reason to look at the calculations, I just want to show that they're elementary, as Sherlock Holmes would say. So now we've defined u at the bottom as log ht of y, and now we define v up there. So now let's have a look at mod ht of y minus this thing. So we're going to be comparing the integral we want with this error function integral I showed you earlier. So having plugged all of this stuff in, all fairly straightforward, we get hty minus this in absolute value is less than this thing down here. So lo and behold, this integral from minus root t on t, ht of y minus this full error integral, this time from minus infinity, is 1 on root t times that thing, plus the error thing outside minus outside t on root t on 2. But if you have a look at the first integral on the here, this is one we can actually calculate. It's finite, as it's less than, well, what we can calculate is the integral from minus infinity to infinity of this stuff. And it is finite, which we can easily verify by substituting and then integrating by parts, and we get the answer 36. So that's finite. So the limit of this, as t tends to infinity, of the first term on the right-hand side is 0. The blue term is finite, and so the limit of that is 0. So we get left with this thing over here. So the limit from here to here is my integral from minus infinity to infinity, e to the minus squared on 2 y squared on 2 dy. And as I indicated earlier, I gave the integral from 0 to infinity. Anyway, this is root 2 pi. So recalling what 8 says, we can combine the top line with equation 8, and lo and behold, we have the limit of this thing is 1. And that's actually the Stirling formula for gamma. It says gamma t plus 1 is asymptotic to this other thing here. So the proof is certainly elementary. It's ugly, and it's really not informative, I don't think. Now, if we did a little more care, we could actually see what the error term was, and we'd see the error is big O of minus n to the minus 1. So most of the proofs in the literature on Stirling's and its extensions prove that they're asymptotic by establishing an error estimate like that. In fact, most of the effort goes into proving these error estimates. Now, in this paper, what I'm presenting now, we observe that once one knows that Stirling's formula is asymptotic, the gamma x plus 1, all of the other known asymptotic formulas can be verified trivially, and I do mean trivially, without the need to establish any error estimates. Now, I'm not saying these other asymptotic formula can be discovered using this observation, but they can be verified using this observation. So let me just go through quickly some of these others, the highlights of these others. So as I said, Burnside quite early had a modest improvement of Stirling's result, namely that first thing in blue here. And we'll see in the table I'll present soon, it really is a very modest improvement. Gosper, on the other hand, published a significant improvement on Stirling and Burnside's formula, and it's not particularly complicated. It's the same level of difficulty as Stirling. Windschitl published in Web Post in 2002 a rather good asymptotic approximation for n factorial, which we can put there. Now, one of the advantages of this is that if you have a calculator, it's particularly easy to use in a calculator. So Windschitl has that advantage. Nemes has an asymptotic approximation similar to Windschitl, similar as good, but better than all of the others at the time. And that's this thing. And again, it's not too complicated. And then Mortici came up with an approximation which is sort of a bit different and also not difficult to plug in the values. Now, Laplace did have a series for gamma x plus 1. This series is the one I've written there. As you can see, the terms get pretty awful pretty quickly. But the ANs and BNs are all can be explicitly calculated and was done so in a paper by Nemes in 2010. It's in my list of references. Namias, who's also in the list of references, says, however, the performance deteriorates as the number of terms is increased beyond a certain value. So we have a look at Laplace's series, called the Stirling series, which we just look up to the term x minus 4, and this thing, which is big enough and awful enough, and see how it compares with the other approximations. As I said, a major advance was really made by Ramanujan, who proved this result here, that gamma x plus 1 equals that, where this theta, he said, goes to 1 as x tends to infinity, and theta lies between 3/10 and 1/10. And he gave some numerical evidence for his claim. If you have a look at Ramanujan's approximation, it's 1 million times better than Gosper's. In 2013, Hirschhorn, who maybe one day we'll write a book on Ramanujan's work, since he's a big fan of that work. He and Villarino proved Ramanujan's claim at least for positive integers and showed that theta n lies between these two values. So we now know Ramanujan's result, at least for positive integers, is true. We don't know for general x. Without explicitly saying it, if you have a look at, as I did, Hirschhorn and Villarino's work, you can get an approximation that's very much better for positive integers n. And so it's better than all of the things that precedes it. And for n equals 1,000,000, it's got a percentage error at least 1,000,000 times better than each one. So 2013, there was a good result. And this term is not so miserable. Chen in 2016 produced a formula which is getting on the awful side with like 53 on 210 in the numerator and so forth. But it's for n equals 1,000,000, it gives a much better result than Hirschhorn and Villarino's. And he says it's order n to the -7. It's error. A more detailed analysis of Hirschhorn and Villarino's improvements suggests a further tweaking is possible, which I did, and I presented it as the first corollary. It's I'm not saying it's terrific, but for n equals 1 to 10,000, it's comparable to Chen's, and for n equals 1,000,000, it's a lot better. Now, let's, without further ado, make what is really a very obvious fact. If you have a function from a subset of R to R, where subject of, from a subset A infinity to R, where A is positive, if the limit of f of x is 1, then gamma of x tends to that. Now that's obvious, because if the first term tends, if you divide that by that, the only thing that matters is the limit of fx is 1. So that's, having said it, it's a triviality that it's true. So what does it tell us? But we need to know Stirling's result, because the proof depends on that. Now we can apply this result and get results better than, well, showing that all of these things are asymptotic, and some of these results, like the one I mentioned for Hirschhorn and Villarino, which are only proved for positive integers, are actually true for all x from this observation, because this theorem I gave here works always, and we know all you need is the limit of fx is 1, and we have the Laplaces versus of Stirling to get the rest of the stage. So Burnside, Gosper lost his R, and Mortici, Ramanujan, Laplace. You can see these various asymptotic formulae, and in each case it's sufficient to determine the function f in theorem 1. That's a triviality to do, and to show, you just inspect them and show that each one of these things has to tend to 1. So all of these results are asymptotic. Once one knows Stirling's result and knows that the thing that you're multiplying Stirling by is something that tends to 1. And I mentioned that you could, almost as a joke, that you could look at this thing where A is some big number, and like Ramanujan, I'm not going to tell you where I got the number. But the point being, it's obvious that this thing, in brackets, all of these things as x goes to infinity disappear, and so we're going to get the right result. Now I'm going to give you some tables which just allows you to compare in actual numbers these things. I use Wolfram Alpha software package. Each of the approximations gets further and further from n factorial as n tends to infinity. So the quality of the approximation is judged by considering 100 times the approximation minus n factorial over n factorial. So let's have a look at table 1. We're almost finished. Table 1, you'll notice, by the way, that when you go down to a million, how giant 10 to the 6th is. The bottom, the first column, it's 8.3 by 10 to the 556. You know, this is certainly a largish number. So Stirling has an error 10 to the minus 6, which is not bad at all. Burnside was, let's say, it's twice as good as Stirling because it's got 4.2 here, but it's still a 10 to the minus 6. Gosper is substantially better because it's now got 10 to the minus 13. When you have a look at Mortici, you're down to 10 to the minus 20. Ramanujan has 10 to the minus 26, which is rather good. Laplace's series, which is extremely ugly, gives you a 10 to the minus 32, and Nemes gives you 10 to the minus 32 as well. Table 3, Windschitl's results, gives you a 10 to the minus 32. The Hirschhorn and Villarino, 10 to the minus 38. Chen, 10 to the minus 4. And the rather silly looking thing I gave gives you a 10 to the minus 50 as an error term. So the bibliography, I'll just run you through it quickly, is Burnside's paper, Chen's, Gosper, Hirschhorn and Villarino, Michel, Mortici, Nemes, Ramanujan, Smith, which I think Smith is where the Windschitl result is actually published, and Tweddle has Stirling's book and annotated translation. Thank you very much.
Thank you very much, Sid. It was really very, very interesting. So if someone has questions, you can unmute the microphone and ask, or you can put your questions in the chat. So keep an eye on the chat. So maybe I can ask the first question just to warm up. Of course, all these estimations of errors, it's really quite impressive. But do you know how actually Stirling found his formula? Because he couldn't use, very powerful results. So he had to probably just, do quite a few experiments with gamblers.
Remember, de Moivre actually essentially had the whole story. He didn't have the C in front, which is root 2 pi. I think Stirling's proof used Wallace theorem, which is on products. So, as I said, if you use more powerful results, you can get these things more easily.
Okay, so just sorry. Yeah, so just looking at the chat, because so there was a question. So a question from Ahmed from France. So I think maybe you know who this Ahmed is. So he's asking for some more papers on this work. So unfortunately, missed the start of the talk.
The actual material is in a paper on archive, which I should be able to get it up again. Can I do that quickly? So it's either in my book, Probability Theory Without Tears, which is on the net, or in the archive paper. And the references, I presume the slides will be available to people after the talk, and the references in the paper give any other information. I mean, the interesting question to me is, and I'll say it's almost an optimization problem, is what is the best F, or what is an optimal F? It is, you know, there's no turn the handle way of producing these F. As I said, once you have an F, you can use my theorem here to immediately see it's asymptotic, but that doesn't tell you how to produce it. Now, the examination of the error term, which, you know, Chen, for example, is so interested in, he points out his is n to the -7, big O n to the -7. You know, I got myself into trouble by saying I'm not impressed with big O n to the anything, because this tells you something converges, and maybe converges better than something else for very large n, but it doesn't tell you what very large is. So is a million very large? So if I tell you this is better than that, and you show something isn't, it could be that I'm just not choosing an n which is big enough. So I'm not sure the big O stuff is very interesting. But anyway, that's a personal view.
I have another question. So once again, while people are warming up, once I actually was working on a project where there was a function which actually included gamma function as, you know, part of a huge ratio. So the question was how to approximate it, and people from this area, I mean from thermal chemistry, something like this. So for me, they're computational chemistry. So they will approximation it by this coefficient x to the power n divided by e to the power x, so right, and then some rational function. So, and I think their intention was to use rational function because it's well known for the flexibility of approximation. So, but now from your talk, I can see that this is actually a natural way to approximate this kind of function, because that's, you know, the best way to approximate gamma function. And as you said, it's not, you don't have to have x 1 million. So the approximation is good enough even for much smaller values of x. So that's basically what I learned from your talk. So to me.
Yeah, and it's certainly surprising. But first of all, one still has to marvel that Stirling or de Moivre's work, you know, produced such an approximation. But it's still very surprising how good it is for even modest size n.
That's right. Yeah. Because once again, in applications like computational chemistry, they don't need 1 million, so they're working with something, I don't know, 50 is enough, 50 is big enough. Okay, I think there is another question from Ahmed in the chat. So, Sid, do you want to read the question? Do you want me to read for you? That's in the chat.
What happens for, we're talking about complex X, is that the one?
Yeah.
Well, if we're proving, the answer has to be yes. That's the short answer. I can't point it, but I don't have any doubt that around the real numbers it's true. Remember that what they're really doing is producing analytical information, and this is by its very nature, the limits are
Sorry, I think you moved a little bit away from the microphone. We couldn't hear very well.
I think there's no doubt that for complex numbers around the reals, this is going to be true. I mean, remember that in extending from the reals to the complexes, one uses analytic continuation. By its very nature, this is saying it's analytic, so the approximations hold. How many people, by the way, knew about the names on the Eiffel Tower? I was then going to say, of those, how many have seen it? But okay. Okay. Well, I thank you for listening and still being here at the end.
And hopefully it will be possible to see those names on the Eiffel Tower at some stage.
That's what I was thinking.
Last I heard, they have no plan of getting rid of it. So, hopefully it will wait for us.
The question is how long to wait.
With French revolutions, I'm not sure that we can guarantee what's going to be there.
Yeah, that's true.
Oh, but the Eiffel Tower is not Notre Dame de Paris. I don't think it will be burned, for example.
Okay, let's be positive. Good point, Nadia.
All right, this was my first Zoom seminar I've actually given. So if you want to privately tell me what could be done differently, then I would welcome that. But thank you.
No, I think it was very, very good. Thank you so much.
Thank you, Sid.
Okay.
Thank you very much. Thank you very much.
Thank you, everyone I know and everyone else. Okay.
Very nice talk.
Thank you. Bye.
Thank you,
Bye.
Sid.